Hello. So the purpose of this video is to introduce the unit circle, where it kind of stems from, and the previous math knowledge that you have that make up the unit circle. So it's instead of me just saying, here's the unit circle, believe me, I'm the teacher, I wanted to kind of dive into its origins a little bit more. And speaking of origins, so this is our unit circle with its radius of 1, and we're already going to go ahead and label some of the important points that we know on this unit circle. Since each of the intercepts that we have here, they're all exactly one away from the origin. By definition of the unit circle, every single point on your unit circle is one away from the origin. And so we actually already know some important points on our unit circle right off the bat. So this, for example, is the point 1 comma 0. This is the point 0 comma 1. Here is -1 comma 0, and then down here is the point 0 comma -1. And those would be just if you graphed regular points on an x and y axis, right? So excuse me, the first point here, 1 comma 0, means that I went 1 to the right, not along my x-axis, and then didn't go up or down at all. 0 comma 1 means I didn't go left or right, and then I went up 1. So that's how you get those points. And those points occur at some particular angles. So, for example, we know that this starting angle that we start with on our unit circle is 0 degrees, or you can write 0 radians. I know that if you went all the way around your unit circle, that'd be 360 degrees, or 2 pi radians. So if I asked you to identify the point on my unit circle at 360 degrees, you should be able to identify this point. Now there are some more special angles that are associated with these other points. So if you go a quarter of a circle, that's 90 degrees, or pi over 2 radians. Half of a circle is 180 degrees, or pi radians, and this should look familiar. This is our conversion factor or conversion proportion we use to change degrees and radians back and forth. And then 3/4 of a circle, 1, 2, 3/4 of a circle is 270 degrees, or 3 pi over 2 radians. And so now we're going to talk about how you get the other points on your unit circle. And there are some pretty important ones that we'll look at. So for example, we'll look at 30 degrees, we'll look at 45 degrees, and then the one I'm going to work off of a little bit here is 60 degrees. So we don't actually need to write the angles right now. They will appear on your unit circle, but we're going to work at 60 degrees. And so what I'm going to draw here is a right triangle, because right triangles have a lot to do with trigonometry, and the proportions of right triangles involve trigonometry, and that's what our unit circle is based off of. So I'm going to show you where they come from, or where the points on the unit circle come from involving trigonometry. So let's do a right triangle. And I'm going to cheat a little bit. Oh, that was pretty close. That was almost 60 degrees where I put that point at. Okay, so here is a right triangle. It's beautiful. It's lovely. And I'm going to actually label or do my sides in a different color. So this one will be blue, and this one will be green. Okay. A couple of things to note first and foremost. This side length here is your hypotenuse. And so my hypotenuse, you actually already know the length of, because as we talked about in the previous video, if I draw my a line from the origin of my unit circle to any side of the unit circle to the outside of the unit circle, automatically those have a radius of 1. So I already know that my hypotenuse length is 1 here. And so then I am going to be working and figuring out what the other lengths are using triangles in a little bit. But for now, we'll call them, this will be side length A, and this will be side length B. So if I was going to write the point that goes up here, you would have to figure out first and foremost how far left and right this point went. So if I was just looking at where this point is, I would say that I went to the right until right here. So that would be I went a length of A. And so the bottom of my right triangle is actually the x coordinate of that point. Whereas my height, if I'm looking at how high or how tall my point is up the y-axis, well, it's actually up a length of b. So your height of your right triangle is the y-coordinate. And so then now we're going to actually be able to figure out in terms of trigonometry what the A and the B represent. And to do this, we have to do a little bit of a flashback to old trig stuff. So we can say old trig stuff. Can be the title of our really fancy notes. And our old trig stuff has to do with SOHCAHTOA. And so that could be a term or a phrase or a chant that you've learned previously. And basically, it's just a mnemonic to remember that if you take the sine of some angle in a right triangle, excuse me, then to find the sine of that angle, you would use your opposite length of the triangle over your hypotenuse length. The ka means that if you're finding cosine of an angle, you're doing your adjacent side length over your hypotenuse. And toa means that if you're finding tangent of an angle, you're doing your opposite side length over the adjacent side length. And so that's what, adjacent. And so that's what those letters mean. The OH, opposite hypotenuse. AH, adjacent hypotenuse. OA, opposite over adjacent. And then they start with the letter that their trig function starts with. So, in this problem, I already said I was going to be working at 60 degrees, and that's because that's this angle that's right here. And so I have this angle in my triangle, and if I were to find, for example, sine of that angle, what I would be finding was I would take my opposite length, so B, divided by my hypotenuse, so 1. So another way I could write this would be that I would be taking my opposite, like I said, opposite triangle side length. So this is opposite of that angle over my hypotenuse. So I'd have B over 1, which is really just B. And so if I'm given an angle, because I won't be given a right triangle in my unit circle, but if I'm given an angle and I would like to find the y coordinate of the point on that unit circle, all I have to do is I have to find sine of that angle. And for cosine, we can do something extra similar. So for cosine, if I'm looking at my angle and I want to find my adjacent side over my hypotenuse, then that gives me A over the number 1, which is just, A. And so if I'm looking for the x coordinate of the point on my unit circle, all I need is cosine of that angle. So as far as the points go, they're made up of sine and cosine. We will dig a little bit more into tangent eventually. For now, it's sufficient to know that if you were going to do tangent of this angle, you would do your opposite side over your hypotenuse. So it would be B over A, or in other words, B I know is sine of theta, and A is cosine of theta. So tangent is really equivalent to doing sine of theta divided by cosine of theta. Awesome. All right, now I want to talk about how we actually would get the point that's right there. So for example, I'm going to go ahead and erase some of the information that we wrote up here already. It might be helpful over here to draw a little note or something like this. So be like the sign is b over 1. It's also our y coordinate of the points on the unit circle. And then cosine is the x coordinate of our points on our unit circle. And then I'm going to do a little bit of erasing because I need to move some of this stuff out of the way. In order to find this point. Okay. All right. So basically I'm going to work still with the 60 degrees, or excuse me, I'll work with the 45 degrees instead. So I'm going to be finding here's 45 degrees. And I'm going to find my sine and my cosine of 45 degrees because then I'll know what my point is right there. So I'm going to find the sine of 45 degrees. And I'm going to find cosine of 45 degrees. And tangent of 45 degrees. And you can plug them into your calculator, but your calculator will spit back an irrational decimal at you. And what we want to find is the exact measurement. And so to do that, we use special right triangles from geometry. So the nice part is, again, I'm not going to be expecting you guys to find them all from special right triangles because we're going to have the unit circle, so the unit circle will give them to you. I just want you to know where this point is coming from when you see it on the unit circle. So in a 45, 45, 90 triangle, the special proportions of that triangle are 1, 1, square root of 2. And so if I'm trying, here's my 45 degree, if I'm trying to find sine of 45 degrees, then I do my opposite side over my hypotenuse. So I would end up with 1 over the square root of 2. For cosine of 45 degrees, I would do my adjacent side over my hypotenuse. So that would give me 1 over the square root of 2. And then if I were to find tangent of 45 degrees, that would give me my opposite side over my adjacent side. So 1 over 1 for tangent. Now these can all be simplified. These two problems, sine and cosine, have to get what we call rationalized, which means that we don't like it when there are square roots in the denominator of our answers. And so we have to make sure, and that's why on your unit circle, you'll never see sine of 45 degrees as this. We have to rationalize. And so to do that, you multiply by that square root that's causing problems on the top and the bottom. And then you multiply straight across the top and the bottom. So then we go 1 times square root of 2 would just give me square root of 2. And square root of 2 times square root of 2 would give me square root of 4, which is just 2. So this is actually what you would see on a unit circle for sine of 45 degrees. So you would see square root of 2 over 2. On our unit circle for cosine, you actually end up getting the same thing, which doesn't always happen. It just happens to be that at 45 degrees. And then tangent isn't in the point itself, so on the unit circle that we'll be using, tangent's just kind of written off to the side out here next to the point. And in a little bit, we're going to go through and look at our beautiful unit circle so we can see how this kind of all combines together. But basically, when we do look at our unit circle, this is where everything comes from. We use either the 45, 45, 90 triangle, or we use the 30, 60, 90 triangle with its proportions to figure out sine of 30 degrees, sine of 60 degrees, cosine of 60 degrees, and so on and so forth. So you're not going to be expected to use special right triangles to find these terms, but I just wanted to let you know that's where these coordinates are coming from, sine and cosine of particular angles using our special right triangles.